Okay, let's talk domain and range some more, right? We've talked domain and range a couple of times this semester so far, so let's do it again, just to make sure we're done. All right, so defining domain. So this is what we're looking at from a graph. From left to right, every x value that has a corresponding y value. Okay, so no holes, right? Holes are not allowed, neither are asymptotes. And what would you say about the range then? We would say that those are the y values. Okay, so the domain is all of your possible x things that you are able to plug into a function or that you have looking at a graph. And the range are all of your outputs, all of the potential y values that come from those x values. So let's look at these ones and let's fill in the domains and the ranges for all of them all at once. Ready? Okay, pause and do that. So there are all of the answers to the first 5, but let's talk about number 6 specifically because it's got some strange things going on here, number 6. So domain one, once again, we go from left to right. So we notice there's an arrow that's going down, but it's also going to the left, which means our domain starts at negative infinity because all the values to the left are going to be included. Now as we come on here, we see that we get to -1 where something is happening. There's an x value right here, so that takes care of -1. And we go until we get to that dashed line at +2. Okay, what do we call that vertically dashed line here at x equals +2? That asymptote is where the y value is undefined at that particular value of x. So we're going to exclude +2 from our domain because there's an asymptote there. There is not a corresponding y value when x equals +2. Okay, so that's okay. We jump over that, and then we come over and we run into this hole at +4. Okay, also we have to jump over that x value because there is not a defined y value that goes along with x equals +4. And then we notice that it goes on forever after +4 to the right, so from 4 to infinity. Okay, so that is one way that we can write this, but there's another way that we're going to talk about for the rest of this video, and that's by using the exclusionary way. Okay, so we have all real values, right? All values are accounted for pretty much from negative infinity to positive infinity. Our graph goes off to the left and our graph goes off to the right. Okay, so for the most part, everything is available except for what two numbers? Except for +2. So we're going to exclude +2 from our domain possibilities, and we're going to exclude +4. So any number you can think of except for +2 and +4. Okay, that's how we're going to start writing our domains when we do it algebraically. We're going to solve for and figure out what numbers do we have to restrict, or what numbers must be excluded based upon a couple of different factors that we're going to be looking at. Okay, so that's where we're going with this, is we're going to change the way we write it. So let's look at some basic functions. Your constant functions, your linear functions, your absolute value functions, and your quadratic functions. If you notice, these all have no domain restrictions, right? A constant line is a horizontal line. A linear function is a diagonally slanted line. The absolute value function is a V, and your quadratic is a U. Okay, there are no holes, no gaps, no asymptotes, no jumps, nothing to restrict your domain. There are no numbers that you need to exclude. So all of these types of functions, every constant function, every linear function, every absolute value function, every quadratic function has all real domain values. There's nothing that you have to exclude from these functions. Okay, but there are a couple that we do have to exclude. One of which is right here. Okay, this is called a rational function because you notice there's an x in your denominator. Okay, so there are some things that you can't divide by, right? We can't divide by 0. If you divide a number by 0, that is an undefined value. You can't chop something into 0 parts. It is just theoretically impossible. Well, maybe it's theoretically possible, but functionally impossible. So we know that the denominator can never be 0. Okay, and this is our key to doing the algebra. Okay, we have to exclude any number that makes our denominator 0 from your domain. We can't plug that number into your equation. So looking at our graph, what would be those two exclusionary values? Okay, hopefully you notice there's an asymptote at the value of -2. So we have to exclude -2 from your domain. We cannot plug -2 into our function, or we're going to get 0 in the denominator. -2 squared is 4. 4 minus 4 is 0. That can't happen, so we exclude -2. And what else do we notice about our graph? There's a hole at +2, which means we also have to exclude +2 from your domain. We cannot plug in +2 or -2 into your denominator, or your denominator will be 0 and your function is undefined. Okay, so there are some restrictions to rational functions. The denominators can't be 0. Now, what type of a function is this little guy? This guy is a square root function. Okay, and what do we know about square roots? Well, hopefully, what do we know what we can't do to square roots? We can't take the square root of a negative number. So we have to exclude all of the numbers, all of the values of x, which will make that equation negative. Okay, so if we're looking at the graph, notice that anything from -infinity is good all the way up until +5. So your domain would be from -infinity to +5 with a bracket on the 5 and a parenthesis on the -infinity. Okay, so we're going to write this rather as x is less than or equal to 5. All numbers less than or equal to 5. Okay, so algebraically speaking, we're going to make equations and solve them so that we can figure out what our domain restrictions are. Okay, because we can't have a negative underneath the radical, so any number that will make that negative, we have to exclude from your domain. And lastly, here we have a cube root function. And looking at the graph, do you see any asymptotes or holes or jumps or anything else that would restrict your domain? And hopefully the answer is no. So these are all real. So there are no domain restrictions on cube roots, only square roots and rational functions. So in practice, what does that make us do, right? Algebra, we want to be able to do something when we are given this information. So it says, how do we determine the domain of a rational function? So based upon what we've talked about, we know that the denominator, in this case, the denominator is given to you by this function h of x. So I'm going to use that notation. We know that the denominator cannot be equal to 0. So we have to exclude any number that makes the denominator 0. So you take whatever equation is in your denominator and you make the equation that it cannot equal 0. And you solve it. And whatever the solutions are to that equation, those are going to be your domain restrictions. Those are the numbers that you have to keep out of your domain. So looking at example number 1. Okay, we are not concerned with the numerator whatsoever in order to find a domain, right? It's nice that it's there, but it doesn't help us. We only are concerned with your denominator. So you take your denominator and you simply make the equation by setting it not equal to 0. Okay, and you set it not equal to because we're trying to exclude it. We can have any x value except for the x's that make your denominator 0. So we're using the not equal to symbol in order to remind us that we are looking for exclusions. What numbers do we have to keep out? Not numbers are we going to include, but what numbers do we have to keep out? So how do we solve this here equation? Well, hopefully you notice that this is already factored, right? This is in some type of a factored form. It's the x minus 3 times x minus 1, and whenever I'm multiplying two things together, that means factored. So if I'm multiplying two things together and getting 0, that means that either the x minus 3 is going to be the 0, or that means that x minus 1 is 0. So you take each of your factors and you set them equal to 0, just like you would solve a quadratic that's factorable. So you take your factors and you set them equal to 0. And we solve each of these individually. So if we solve this one, we know that x cannot be positive 3. Because if x is positive 3, 3 minus 3 is 0. 0 times 2 is 0, right? Can't happen. So we have to keep positive 3 out of our domain. And what's the other number we have to keep out? Positive 1. Because 1 minus 3, well, that's negative 2. But 1 minus 1 is 0. Negative 2 times 1 is 0. And you can't have 0 in your denominator. Okay, so we can be formal, and we'll write the domain as all real values as long as x does not equal positive 3 or positive 1. Okay, and they often put these in these curly brackets or these mustaches as a way to represent the domain. Okay, you won't always see it like that, but you might see it like that. So that's how we're going to write it just for today. So let's look at number 2. Here we have our rational equation. It has an x in the denominator, so that makes it rational. And you set your denominator not equal to 0. Whatever number makes your denominator 0, we have to exclude, which is why we have the not equal to in there. And let's solve this. We're going to solve this by, well, we're going to solve it straight away. Okay, so x squared cannot be equal to positive 9. And we solve a square by taking the square root. So one of the square roots of 9 is positive 3. Okay, but as you hopefully you know from your quadratics that if you draw a horizontal line through any quadratic, how many times does it cross? Crosses 2 times. So how many answers should we be expecting when we take the square root? We should be expecting 2 answers. One of them is positive 3, the obvious one. The other one is negative 3, the less obvious one. Okay, so if x crosses at positive 3, x will also cross at negative 3, right? These come together as a conjugate pair. When you take the square roots in algebra, when you're solving, you get positives and negatives. So we have any real value in the entire world as long as we are excluding a positive and negative 3. Okay, any of them, right? Which is the easiest way to write this. Rather than as an interval with a couple of different u's, we're going to write it as 1. Okay, moving on to the most difficult one in our examples. We're going to set this denominator not equal to 0. Right, because we're not concerned about the numerator at all. So what type of an equation are we given here? Quadratic. This is definitely a quadratic equation, right? So we can't solve it by square rooting. We have to hopefully solve it by factoring. So we're going to factor this quadratic. So we draw in your parentheses, right, that represent your factors. And the numbers in front, right, your variables go in front. So you want to think about what numbers multiply together to give you 2x squared. Okay, hopefully you know one of them is 2x and the other one is regular x. Okay, 2x and regular x. So that when I multiply these back together, 2x times x is 2x squared. Okay, now the last number in your factor, the number that goes here, these two numbers have to multiply to give you negative 3. If the first numbers multiply to give you the first thing, then the last numbers multiply to give you the last thing. So we want to think, what numbers multiply to give us negative 3? And hopefully you're thinking that they're negative 1 and positive 3, or positive 1 and negative 3. So we have to put those numbers in here and in there and see which one works out, right? So this is trial and error. If you don't succeed, try something else. So what if we put a -3 here and a +1 there, right? Just trying it. Not saying it's going to work, but let's try it. So we have to FOIL, right? Here's your 2x squared, check. There's your -3, but then we need to do the O and the I to get -5. So 2 times 1, that's 2x, and then -3x. I don't think this is going to work out. Do you think it's going to work out? Right, what is -3x plus 2x? Well, it's not -5x, right? So that means we got our factors wrong. So let's go ahead and get rid of all that stuff. That means we have to retry something. Let's just, what else should we try? Let's just switch them. What if we had a +1 here and a -3? Okay, let's see what that would do, right? We're going to try it. If it doesn't work, we have an eraser. What's 2x times -3x? Well, that's -6x. And what's 1 times x? Well, that's just 1x. So then what does -6x and +1x give you? Oh, that gives you -5x, which means that these are, in fact, your correct factors. 2x plus 1 and x minus 3. Those are the correct factors, because when you FOIL it back out, you get this quadratic that we started with. Okay, that's probably the hardest part, whether you're good at factoring or not, is factoring. So 2x plus 1, that can't be 0, or x minus 3. These are our two numbers that we have to exclude from your domain. So when we solve this, we get -1/2, and when we solve this, we get x can't be +3. So here are your two exclusionaries, any real number except for -1/2 or +3. So our other ones are the square roots. Okay, so I'm going to use this notation, right? G of x represents your radicand. That's the thing underneath your radical is the radicand. So what we said is your radicand must be non-negative. So you take whatever is underneath your radical and you make an equation by setting it greater than or equal to 0. So let's see what that looks like in practice. Okay, so this is your radicand, the x plus 3. It's underneath your radical. So we set x plus 3 must be greater than or equal to 0. Okay, that's your equation that we're going to now solve for x. So we'll subtract 3 from both sides, and we get that x has to be greater than or equal to -3. Any value. So we could write this right as an interval. This is how we're used to writing it, from -3 to infinity. Right? Graphically speaking, it would be moved 3 units to the left. That's what this transformation does, but it opens to the right because it's positive. So look, all of our graphs checks out, your domain checks out, your interval checks out. It all works together to give you the domain of root x plus 3. Okay, so the process is whatever is underneath your radical, you set it greater than or equal to 0, and you solve. So in solving, I know there's rules to this, but if you keep x positive, so I'm going to add 2x to both sides, because sometimes I forget about these rules of, actually no, I don't forget ever. I know all of them. I've practiced them enough that they're in my brain. But I like to keep x positive, so I'm going to add 2x to the right side, and then I just divide by 2. So if I don't want to remember the rule about dividing by a negative, if you keep x on the left, okay, then just keep x positive and your inequality never has to change. So this is all numbers greater than or equal to +2. Okay, so this would be your interval. And if we remember, right, this moves the graph 4 units to the right, but then our negative means it opens to the left in the negative direction. So we would go 2 units to the right, and it would open this direction. So that's how these work, right? So we have a negative infinity to 2 domain. You cannot plug in any number greater than positive 2 or your radical will be negative. And lastly, once again, you take your 3x plus 1, you set it greater than or equal to 0, and you do all of your wonderful math in order to solve this equation down. So x has to be greater than or equal to negative 1/3. Okay? So what happens if I have mixed things? So here I have the cubics, right? The domain of a cubic is just all reals. There's nothing that we have to restrict there. So all reals, all reals, all reals, until we get to this one. Number 3 is the cube root of a rational. So notice we have a rational function in here. Well, you still can't take the cube root of an undefined value. So we still have to figure out what numbers make that fraction undefined, because you can't take the cube root of something that's undefined. Okay, so we're going to take your denominator, even though it's underneath a radical, the cube root, which doesn't have any restrictions, and we are going to figure out what makes this one undefined. Okay, and we have to keep out whatever value that happens to be. So negative 1/2 is the only value that we have to exclude from our range or our domain in order to make that h value a good value. Okay, so there are 2 functions that we are looking for when it comes to domain restrictions: rationals and square roots. So if you see a rational, you set your denominator not equal to 0 and you solve. And if you have a square root, you make your radicand greater than or equal to 0 and you solve. Okay, so there's some stuff about finding domains using algebra.